Hello there. I'm so glad our paths crossed in this quiet space tonight. Allow the edges of your day to soften and the light around you to dim into a comfortable, easy, dark. No need to chase any lingering thoughts. Just let them float by like distant clouds. Wherever you are, I hope you feel held in this shared moment of stillness, unhurried and calm. Tonight, we're setting out on an utterly gentle journey. We'll be gliding past some of the most dramatic, high-contrast objects the universe holds, the places where the laws of physics are pushed to their very breaking point. Think of them as the silent, powerful extremes of the cosmos, entities so massive, so intense, they shape space and time just by existing. We won't rush. We'll simply let the scale of their mystery settle softly into your mind. There is a deep, soothing wonder in contemplating something truly immense from the safety of your own quiet room. If this kind of soft wondering brings you a sense of peace, a quiet like, and a soft subscribe, truly help other sleepy souls find their way to this stillness, too. For now, let the velvet darkness of the night sky take hold. When you're ready, we'll begin our hushed exploration together. Out in the dark, the universe is full of worlds that would never feel like home. Some are small, rocky planets not so different in size from our own, circling quiet stars in wide, cold orbits. Others are swollen giants of gas, bloated and bright, or collapsed stars so dense that a teaspoon of their matter would outweigh a mountain. From far away, they are just points of light, tiny marks on an astronomer's chart. Up close, many of them would be deadly to us in ways that are hard to even imagine. Most of the cosmos is not designed with human comfort in mind. Temperatures swing from almost absolute zero to millions of degrees. Atmospheres can be made of glass, iron, or boiling acid. Gravity can be so weak you would float away, or so strong that your body would be pulled apart in less than a heartbeat. And yet, even in this harsh crowd, a few places stand out as especially dangerous, like sharp thorns hidden in an already hostile garden. Astronomers sometimes lean into that sense of danger in a playful way. Around a late October a few years ago, close to Halloween, NASA gathered a small gallery of the most frightening worlds we've found so far. It was a way of reminding us that space is not only beautiful and mysterious, but also extreme and unforgiving. Among that eerie collection were several exoplanets, worlds circling other stars that are not just uncomfortable, but truly lethal. On some of them, simply drifting nearby in a ship would be enough to spell the end. Imagine, then, that we are moving through that list together, not in a real spacecraft, but in a quiet, unhurried way, like two friends pointing out faraway storms from the safety of a dark hillside. Each world is distant. Each one is, for us, safely unreachable. But we can still wander past them in our minds and feel the chill that comes from knowing what they are like. The first world on this strange tour is a giant made almost entirely of gas, known to astronomers as TRES 2b. It orbits a yellow star similar to our sun, a star called TRES 2, far away from us, hundreds of light years across the dark. If you could stand at some impossible observation deck nearby and look straight at this planet, you would barely see it at all. TRES 2b is the darkest exoplanet we've ever found. Its atmosphere, rich in unfamiliar chemicals, swallows nearly all the light that falls on it. More than 99% of the starlight that hits its clouds is simply absorbed, melted into heat, instead of reflected back into space. Most planets, even gas giants, give some of that light back. Jupiter, for example, reflects enough sunlight that we can see it easily with the naked eye from Earth. TRES 2b, by contrast, is like a drop of ink floating in the void. Up close, its darkness would not be perfectly complete. The planet is heated to nearly 1,000 degrees Celsius, baked by its star and squeezed by its own gravity. That heat makes it glow very faintly, like embers buried deep under ash. If your eyes could adjust, you might see a dull, red smear where the planet hangs, more suggestion than shape. No clouds, no swirling storms, no easily visible bands like those on Jupiter, just a heavy, smothering blackness with the thinnest outline of red. Astronomers think that some unusual reactions in its atmosphere are responsible for this behavior. There may be vapors there that we have never seen in such conditions before, slowly eating the light in ways we don't fully understand yet. TRES 2b has a mass a bit greater than Jupiter's and a slightly larger radius, so it is huge compared to Earth, a true giant. But its size is not the most frightening thing about it. What is unsettling is how it seems to almost erase itself from sight, as if it prefers to exist as a kind of absence. Still, for all its unnerving darkness, TRES 2b is not the most dangerous place the universe has to offer. A ship that somehow managed to float at a safe distance from the planet's atmosphere would not be immediately torn apart. You would be roasted by heat and bathed in unpleasant radiation. But in the grand scale of cosmic horrors, this world is more eerie than truly vicious. There are other planets whose very nature is more violently hostile, where matter itself seems to be in a state of constant agony. So let the dark giant drift behind us, shrinking back into a tiny, invisible shadow next to its distant star. Ahead, another point of light waits, a system not so unlike our own, with a star that looks friendly enough at first glance. This one is called 55 Cancri, and around it circles a set of planets, some gentler, some harsher. Among them is one world that has captured a lot of attention, a planet named 55 Cancri E, where TRES 2b was vast and smothered in gas. 55 Cancri E is much more compact and dense. It is a rocky super-Earth with a mass around 8 times that of our planet and a radius not quite twice as large. On paper, that might sound almost familiar, as if it could be a heavy cousin of Earth. But the resemblance ends the moment you look at where it lives and how it moves. This world orbits extremely close to its star, far closer than Mercury does to our Sunday. The distance between 55 Cancri E and its sun-like star is only a tiny fraction of the Earth-Sun separation. At such a short distance, gravity has locked the planet's rotation so that one side always faces the star and the other side always faces away, the way the same face of the moon always looks at Earth. The result is a world with a permanent day side and a permanent night side, with no sunrise and no sunset anywhere on its surface. On the side that looks straight into the star, temperatures reach around 2,400 degrees Celsius, hot enough to melt most rocks, to turn the ground into oceans or lakes of lava. The night side is cooler, but only in a relative sense. It still sits at well over 1,000 degrees. There are no calm, dark, frozen plains here, only a slightly less brutal heat. Under such conditions, any solid crust is likely to be thin and restless, broken open by constant volcanic activity. Scientists suspect that 55 Cancri E may be wrapped in a thick atmosphere made of lighter gases like hydrogen and helium, along with heavier compounds rich in carbon. Volcanic eruptions could throw immense clouds of dust and vapor high above the surface, forming shrouds that move slowly around the planet. These clouds can trap heat like a blanket, making the day side even more unbearable and preventing the night side from ever truly cooling down. If you could hover above the surface, you might see rivers of glowing rock, storms of ash, and horizons that never darken. Deep inside, where pressures climb to almost unimaginable levels, that carbon may be forged into layers of pure crystal. Some models suggest that a large part of 55 Cancri E's interior could be made of diamond, an entire world with a heart of glittering stone, hidden beneath a shell of fire and smoke. It sounds beautiful, but there is no way to touch that beauty. Any material we know would vaporize long before it reached those depths. The 55 Cancri system holds other planets that are far more forgiving, at least in theory, worlds where temperatures and conditions might be closer to something we recognize. In that sense, this system is a little like a neighborhood where one house is quietly on fire all the time, while the others sit in relative peace. That contrast makes 55 Cancri E stand out even more sharply, a reminder that danger can exist right alongside calm in the same small patch of space. If we move our gaze again, we find another kind of danger, less about heat and lava and more about the company a planet keeps. Some worlds do not orbit ordinary, steady stars at all. Instead, they circle the remnants of stars that have already died. One such planet carries a name borrowed from ghost stories: Poltergeist, also known by its catalog label PSRB 1257+12c. This planet orbits a pulsar, the collapsed core of a massive star that once ended its life in a supernova. When such a star dies, its outer layers are flung into space in a titanic explosion, leaving behind a dense, spinning sphere made mostly of neutrons. That neutron star rotates rapidly and sends out beams of radiation from its magnetic poles. As it spins, those beams sweep across space like the light from a lighthouse, and if one of them passes over Earth, we see a regular pulse. That is why we call these objects pulsars. Poltergeist lives very close to its pulsar, at a distance much smaller than Earth's orbit, closer even than Mercury is to our Sunday. To survive the supernova that created the pulsar would have been almost impossible, so scientists think this planet must have formed afterward, from the debris the explosion left behind or from matter dragged in by the intense gravity. However it was born, it now circles a dead star that behaves like a cosmic siren, blasting out radiation with every turn. The planet itself is thought to be several times more massive than Earth, with a year that lasts only about 66 of our days. Those are just numbers on a page. The real story is in the environment. The pulsar's radiation is fierce, filling the space around it with particles and high-energy light that would strip the atmosphere from an ordinary planet and tear apart complex molecules. Any spaceship daring to approach would be hammered by this invisible hail, its shields and hull stressed to the breaking point long before it reached orbit. There is a strange, lonely poetry in the idea of a planet circling such a star, a world built in the ashes of a catastrophe, lit not by warm, steady daylight, but by harsh pulses from a corpse of a sun. If Tres 2b felt like an absence of light, and 55 Cancri E felt like too much heat, Poltergeist feels like exposure, raw, unfiltered radiation in a place where life, as we know it, would have no shelter. Yet even here, the universe is not done raising the temperature. There is another exoplanet, known as Kepler 70b, that pushes the idea of heat to an extreme. Where Poltergeist orbits a dead star, Kepler 70b skims the surface of a star that is very much alive, but has changed in dramatic ways. Its host is a hot subdwarf, a star that has already shed much of its outer layers and burns with a blistering surface temperature hotter than that of our Sun, around 6,800 degrees Celsius. Kepler 70b races around this star so closely that its orbit is measured not in millions of kilometers, but in a tight loop that would fit comfortably inside the orbit of Mercury many times over. Its year lasts only a matter of hours. At such a short distance, the planet is exposed to an intense flood of energy. Its own surface is estimated to be one of the hottest known for any rocky planet, hot enough that metals like iron and titanium could exist as vapor in its upper layers. If you could somehow look down on Kepler 70b from above, you might see it as a small, glowing bead hurtling around a brilliant white-blue star, racing so fast that it completes a full circle in less than a single Earth day. There would be no solid ground as we understand it, only a tortured, possibly partially melted crust, perhaps even relics of a former gas giant whose outer layers were stripped away when the star swelled in an earlier phase of its life. Any nearby visitor would be blasted not only by light, but by fierce stellar winds and streams of charged particles. Matter here does not have much chance to rest. It is heated, stripped, and reshaped again and again. Compared to this, the heat of Mercury, or the hottest deserts on Earth, feel like a cool evening. From the darkness of Tres 2b to the lava glare of 55 Cancri, from the ghost-lit orbit of Poltergeist to the furnace of Kepler 70b. These worlds sketch out just a tiny slice of the universe's imagination. They are reminders that planet does not necessarily mean place you could stand, and star does not always mean a gentle source of light in the sky. Out there, danger takes many forms: shadow, fire, radiation, and heat so intense that rock flows like water. And within that crowded gallery of hostile worlds, there is one small ember of a planet that seems to push heat and nearness to a star almost as far as a rocky world can go. From far away, this world, Kepler 70b, is just another point in the darkness, a small companion racing around its fierce star. Up close, if we could ever stand at a safe distance and watch it, we would see a compact ember of rock, not a swollen giant. It is smaller and lighter than Earth, dense and tightly bound, circling its star so quickly that a full orbit takes only about 5.5 hours. A day and a year blur into almost the same thing there, time wrapped into a tight loop around a burning sun. That orbit is not only fast but also crowded. Kepler 70b shares its system with another planet, Kepler 70c, and the two of them sweep past one another at a distance of only about 240,000 kilometers, roughly the gap between Earth and our moon. Each time they pass, gravity tugs at both of them, flexing their interiors and stirring tides not of water, but of stone. The temperature on Kepler 70b is so extreme that ordinary words like hot begin to lose their meaning. Bathed in fierce radiation from its star, its surface may be heated to thousands of degrees, easily enough to melt and vaporize rock. Some astronomers suspect that this planet might once have been part of the star itself, a larger world or outer layer, slowly stripped away as the star changed and shed its skin. In that picture, Kepler 70b is not just a planet but a remnant, a scar left behind by an older act of violence. Because of this unusual history, there is still some quiet doubt about exactly how we should describe it. The data we have are delicate, pulled from faint patterns in starlight, and some details are still being debated. It may be that what we now call Kepler 70b will someday be understood differently as our instruments sharpen and our models improve. For now, though, it stands for a certain kind of world, one that skims so close to its star that matter itself struggles to remain solid. Kepler 70b is not alone in this strange category. There are other planets that have wandered so close to their suns that they are now being slowly unmade. One of the most haunting examples is a gas giant known as WASP-12b. This world is enormous, almost twice the size of Jupiter, and more massive too, but it orbits its star at a distance that feels alarmingly small, only a few percent of the Earth-Sun separation. At that distance, the star's gravity does not simply hold the planet in place, it stretches it. WASP-12b is being pulled into an elongated shape, like a drop of water on the verge of falling. Its atmosphere is heated to well over 2,000 degrees Celsius, glowing and thinning at the edges where gas is beginning to slip away. That gas spirals toward the star, forming a faint stream of stolen matter. If we could watch this system in a sped-up time-lapse over millions of years instead of human lifetimes, we would see WASP-12b shrinking as its outer layers are peeled away. Astronomers estimate that in about 10 million years, an instant in cosmic terms, this planet may be gone entirely, devoured by the star it once circled. Because planets like this are so hostile and so fragile, it is easy to imagine that they would never be more than curiosities to us. We will probably never send probes to orbit them, never map their surfaces in detail, never see them the way we see the gentle clouds of Jupiter or the craters of Mars. And yet, even these doomed giants have something important to offer. In the way their atmospheres stretch and tear, in the way they glow and dim, they tell us how gravity and light shape matter at the very edges of stability. Danger in the universe is not always obvious at first glance. Some worlds look surprisingly familiar from a distance, wearing colors that we associate with calm and safety. One such planet is HD 189733b, a gas giant only about 63 light-years away, orbiting an orange star in the small constellation of Vulpecula. When astronomers first studied its light, they found that the planet appears a deep, vivid blue, not unlike the color of Earth when seen from space. From far away, it would be tempting to imagine oceans, skies, and the cool hush of water beneath clouds. But HD 189733b is not an ocean world at all. It is a hot Jupiter, roughly the same size and mass as our own Jupiter, circling much closer to its star than Mercury does to the Sunday. Its orbit takes only a couple of days to complete, and it is almost certainly tidally locked, with one side always staring into the star's glare and the other side forever turned away. The beautiful blue color does not come from water, but from light scattering off tiny particles held in a violently moving atmosphere. On the day side, temperatures soar to hundreds of degrees Celsius, hot enough to turn many minerals into vapor. On the night side, the air never cools to anything we would call comfortable. It remains searing, just somewhat less extreme. Between these two halves, winds race at extraordinary speeds, reaching thousands of kilometers per hour. These winds do not merely move air, they carry grains of silicate, the same kind of material that makes up glass and sand on Earth. Imagine a storm where the air itself is laced with ground glass and the wind howls at several thousand kilometers an hour. In such a place, there is no safe direction to face, no shelter to hide behind, only an endless, abrasive rush. Models suggest that in some regions of HD 189733b, the atmosphere could produce rain made of molten glass, falling sideways rather than down as it is driven by those ferocious winds. It is a blue world, yes, but one of glass and fire rather than water and sky, because this planet passes directly between its star and us as it orbits. It offers astronomers a rare opportunity. With instruments like the Hubble Space Telescope, they can watch starlight filter through the thin shell of its atmosphere during a transit. As that light passes through, different molecules absorb different colors, leaving faint signatures in the spectrum. By studying those signatures, scientists can begin to piece together what the atmosphere is made of, even though no one can ever go there. Those observations revealed that HD 189733b has a hazy, fog-like atmosphere. When the planet transits, the edge of its atmosphere can take on a reddish tint, as if lit by a perpetual sunset. That color shift likely comes from tiny particles, perhaps iron-rich dust, silicate grains, and aluminum oxide suspended high above the deeper layers. These particles scatter blue light in some directions and let redder light pass through in others. Deeper in the atmospheric mix, astronomers have found traces of water vapor, neutral oxygen, and simple organic molecules like methane. They have also detected carbon monoxide, especially on the hotter day side, hinting at complex chemistry driven by intense heat and light. One of the most intriguing findings involves methane in a strange, energized state, glowing in infrared wavelengths in a way that does not quite match our expectations. This fluorescent methane suggests that something unusual is happening in the upper atmosphere of HD 189733b, perhaps involving powerful electric fields, strong shocks in the wind, or intense ultraviolet radiation from the star. We do not yet know the full story. What we do know is that by studying even such a harsh, inhospitable place, we are learning about physical and chemical processes that may also occur more quietly in other corners of the universe. Worlds like these are sometimes nicknamed horror planets, and it is easy to see why. Between glass storms, evaporating giants, and rock melted into vapor, they read like nightmare versions of familiar places. But they also serve as mirrors, reflecting back to us the quiet good fortune of our own position. Our Earth, with its mild temperatures and stable star, begins to look not ordinary at all, but exquisitely balanced. As our surveys of the sky continue, the list of extreme worlds grows longer. Some planets fry so close to radiation that their surfaces become seas of lava. Others huddle near dead stars that bathe them in beams of high-energy particles. There is no single way for a world to be dangerous. The universe is endlessly inventive in that regard. Even so, the catalog is far from complete. There are planets whose dangers we have only begun to guess at, tucked close to small, dim stars that do not stand out in the sky. One such system lies about 200 light-years away, anchored by an orange dwarf star called K-141. This star is smaller and cooler than our Sun, with a somewhat lower temperature and with a mass and radius modestly reduced. It burns steadily, more modestly than our Sun, yet still powerful enough to shape the fates of any nearby planets. Hugging this star at an astonishingly close distance is a rocky planet known as K-141b. The gap between planet and star is only a tiny fraction of the distance between Earth and the Sun, so small that by our standards, it hardly feels like space at all. The planet's orbit is so tight that it completes a full circle in about 6.5 hours. A year there could pass over the course of a single evening here, with sunrise, noon, and sunset all folded into one brief sweep around the star. K-141b is heavier and slightly larger than Earth, with a mass about 5 times greater and a radius about 1.5 times as big. That combination means that gravity at its surface would be at least twice as strong as what we feel under our own feet. Walking, if it were ever possible, would feel like carrying a heavy pack you could never take off, every step pressing you harder into the ground. Inside, a large fraction of the planet's mass, perhaps between 1/5 and 1/2, is thought to be locked up in a dense metallic core. All of this, the close orbit, the strong gravity, the heavy core, creates conditions that are anything but gentle. K-141b, like many close-in rocky worlds, is almost certainly tidally locked, forever turning the same face toward its star. One hemisphere bakes in relentless light, while the other is plunged into endless night. At the border between them, at the thin ring of eternal sunrise, temperatures and pressures may shift dramatically over just a short distance, driving winds and flows of material that are unlike anything on Earth. From the quiet distance of our own orbit, we can only imagine what such a world might truly be like. The numbers, mass, radius, orbital period are just the bare bones of a story that our minds try to clothe with skies and horizons. On K-141b, those horizons are likely shaped not by rivers of water or slow sheets of ice, but by the direct touch of starlight on bare rock, melting, evaporating, and refreezing it in a relentless cycle. If we lean in a little closer, still wrapped in our own soft dark, we can begin to picture how deeply that nearness to a star can rewrite the idea of a planet's surface. On a world like K-141b, being so close to its star changes almost everything about what surface and sky even mean. The planet is chained to its star by tidal forces so strong that it always shows the same face, the way our moon always turns one side toward Earth. One hemisphere is locked in endless day, held forever in the orange glare, while the other lies in an unbroken night that never knows sunrise. There is no gentle daily cycle there, no routine warming and cooling, only a stark, permanent divide between scorching light and deep shadow. On the day side, temperatures climb to around 3,000 degrees Celsius, hot enough not only to melt most rocks and metals, but to begin turning them into vapor. In that kind of heat, the ground does not behave much like solid ground at all. Instead, Scientists think the illuminated half of K2141b may be covered by an ocean of lava, endless, roiling, and bright, a sea of molten rock, stirred constantly by the star's relentless glare. Above that ocean, the air would not be the kind we know, but a strange vapor made of evaporated stone, heavy with silicates and metals that have been boiled straight off the surface. Far across the Terminator line, on the other side of the planet, the story is completely different. Deprived of direct starlight, most of the night side cools drastically. Temperatures there are calculated to be dozens of times lower than on the day side, dropping well below freezing for many materials. Rock that was gas or liquid under the star's gaze can become solid again in this quiet, dark, forming crusts and plains that never see the sky brighten. It is as if one world of fire has been fused to another world of ice, joined back to back and left to circle in silence. The brutal contrast between these two halves does more than paint a dramatic picture. It sets the entire atmosphere into motion. Models suggest that the temperature difference drives winds that race from the day side toward the night side at speeds of nearly 2 kilometers per second. That is around 5 times the speed of sound in air on Earth. If we could somehow stand in that wind, ignoring, for a moment, the heat and the lava, it would be a deafening, continuous roar, the planet's own atmosphere screaming as it is yanked from one extreme to the other. As the vapor of rock and metal is swept into the darkness, it begins to cool. In the twilight regions near the border between day and night, that vapor is thought to condense into droplets and shards, forming a kind of fiery rain. Instead of water falling into oceans, you have molten minerals raining down onto blackened crust, pooling into glowing rivers that flow back toward the hotter regions. Eventually, this molten material returns to the dayside's lava ocean, where it evaporates once more, feeding the atmosphere again. In this way, K2141b may host a complete rock cycle. In the most literal sense, a weather system made of stone, endlessly evaporating, condensing, and flowing. This strange circulation likely touches only parts of the planet. The rock vapor lifted from the day side probably cannot travel all the way to the deepest, coldest parts of the night hemisphere before it condenses and falls. That means there may be a band around the Terminator where the fiery rain and lava rivers are most active, while the central regions of the night side remain locked in a more stable cold. There, far from the star's reach, and beyond the direct influence of the lava ocean, the ground might be a frozen desert of solid rock, cracked and silent beneath a thin, exotic sky. Even so, K2141b is not the hottest world we know. There are planets that take this theme of heat and closeness and push it even further, to the point where their very atmospheres begin to resemble the glowing outer layers of stars. One of them orbits a fiercely bright star about 670 light-years away in a distant corner of the sky. Astronomers call this planet Kelt 9b, and in many ways, it blurs the line between planet and star in a way that feels almost unsettling. Kelt 9b is a gas giant with a mass nearly 3 times that of Jupiter and a radius roughly twice as large. But instead of drifting in a wide, cool orbit, it hugs its parent star at a distance that is only a small fraction of Earth's path around the Sunday. It completes a full orbit in about a day and a half. At that range, the planet is immersed in a blistering bath of radiation. Its dayside temperature is measured at around 4,600 Kelvin, which corresponds to well over 4,000 degrees Celsius hotter than the surfaces of many red dwarf stars. Its host star, Kelt 9, burns as a bluish-white beacon, more massive and larger than the Sunday. With a mass roughly 2.5 times that of our star and a radius more than twice as wide, it shines with a surface temperature of around 10,000 Kelvin, nearly twice as hot as the sun's outer layers. That kind of star pours out intense ultraviolet light, the sort that can strip electrons from atoms and batter molecules into fragments. Kelt 9b, so close that it feels almost pressed up against this furnace, lives in a constant storm of energy. In the depths of its atmosphere, conditions are even more extreme. Calculations suggest that parts of Kelt 9b's upper layers can reach temperatures of around 11,000 Kelvin. At those temperatures, even heavy metals like iron and titanium do not remain locked into solid grains. They can exist as vapor, drifting among lighter gases like hydrogen and helium. The planet's atmosphere is not just hot, it is ionized, with atoms losing electrons and becoming charged particles that respond to fields and flows in complicated ways. This superheated atmosphere does not stay put. The intense radiation and the star's powerful winds gradually strip gas away from the planet, blowing it out into surrounding space. Observations indicate that Kelt 9b is wrapped in a cloud of thin, escaping material, a kind of shimmering envelope of atoms on their way out. Over long stretches of time, the planet is expected to lose mass at a remarkable rate, shedding the equivalent of many Earths' worth of gas every billion years. If we let our thoughts run ahead by tens or hundreds of millions of years, we can imagine Kelt 9b slowly thinning, its outer layers peeled away by the star's relentless touch. Perhaps, eventually, only a dense core of heavier elements will remain, a stripped-down remnant where a gas giant used to be. But the star itself is not immortal. Massive, hot stars like Kelt 9 burn through their fuel quickly, long before the planet has fully transformed into a bare core. Its host may swell and change, entering later stages of its life and finally engulfing the worlds that orbit too close. In K2 141b and Kelt 9b, we see two ways that a star can take apart a planet: by melting its rocks into vapor and by blasting its atmosphere into space. They are, in a sense, worlds in the process of being undone, caught halfway between their birth and their eventual disappearance. Yet not all stories of stars and planets end this way. Some worlds endure their stars' most violent transformations and emerge on the other side, changed, but still there. Far beyond these superheated systems, more than 4,500 light-years from Earth, lives a small, intensely hot star known as V391 Pegasi. Today, it is a compact remnant, no longer a full-size star like the Sunday. Its mass is roughly half that of the Sun, and its radius only a fraction, about a quarter of the Sun's size. Despite its modest dimensions, its surface glows at nearly 30,000 Kelvin, 10 times hotter than a pleasant yellow photosphere. It is a star that has burned through its main fuel and shed much of its outer material, beginning the long, slow journey of cooling that will eventually lead, far in the future, to a faint and quiet state. Around this small, fierce ember orbits a planet called V391 Pegasi b. Today, it appears to be a gas giant with a mass around 3 times that of Jupiter, circling the star at a distance of about 1.7 astronomical units, farther than Earth is from the Sunday. It takes roughly 3 Earth years to complete one orbit, gliding in a slow ellipse through the glare of a star that is hot but no longer large. On the surface, those numbers might not seem unusual. We are used to gas giants in wide orbits. What makes this world remarkable is what it has already lived through. To understand its story, we have to imagine the earlier life of its star, V391. Pegasi was once a more ordinary star, burning hydrogen in its core and shining with a steadier light. In time, as with all such stars, it exhausted that central fuel. With the core shrinking and heating, the outer layers expanded and thinned, and the star swelled into a red giant. In that swollen state, its outer atmosphere puffed out to many times its original size, becoming so extended and rarefied that it reached close to and possibly beyond the orbit where V391 Pegasi b now travels. In that phase, the planet would have found itself moving not around a tidy, compact star, but through the star's own diffuse outer layers, a sea of thin, hot gas. The densities there were lower than the air we breathe by many orders of magnitude, but encountering any material at orbital speeds over and over again takes a toll. The planet would have been plowing through this envelope, losing orbital energy as it felt drag from the star's extended atmosphere, gradually spiraling inward. Under many circumstances, this kind of interaction ends badly for the planet. It can be pulled deeper and deeper into the star, passed from thinner, outer layers into hotter, denser regions, where its atmosphere is stripped away and its solid or liquid core is ultimately broken apart. But in this particular system, the timing worked out differently. Before V391, Pegasi b could be fully consumed, the star shed its outer layers into space, throwing them off in a dramatic wind and leaving its hot, compact core behind. What emerged was the star we see now, small, scorching, and slowly cooling, with a planet still in orbit around it. That planet must have lost some energy and perhaps some mass during its passage through the extended stellar envelope, but it survived as a whole object. It now moves through a region where the star's gravity is still strong but no longer buffered by thick layers of gas. Its continued existence is a quiet proof that at least some planets can live through their star's most violent changes. There is still much we do not know about exactly how V391 Pegasi b weathered that ordeal, the amount of its atmosphere that was stripped away, the degree to which its orbit shrank or changed shape, and the precise path it took through the star's former envelope are all questions that models are still trying to untangle. What is clear is that its present mass is still substantial, and its orbit is still wide enough to keep it out of the star's current reach. In this one system, the universe has shown us a different kind of danger and a different kind of resilience. Kelt 9b and K2141b feel like worlds being steadily erased, undone by steady, relentless heat. V391 Pegasi b feels like a survivor, a world that passed through a star's dying breath and emerged, altered but intact. Together, they sketch a picture of just how deeply a star can shape the fate of the planets that fall under its influence, from gently warming them to boiling them away, to briefly swallowing them and then letting them go. Drifting among these stories in your imagination, it becomes easier to sense how fragile and precious our own circumstances are. We orbit a star that is neither too hot nor too cold, at a distance where rock stays solid and water can flow as liquid, under an atmosphere that does not tear itself apart or rain down glass. We are not skimming a stellar furnace, not crossing the ghostly outer layers of a dying sun, not bound to a lava ocean beneath a sky of vaporized stone. In the quiet of the night, with these distant, dangerous worlds held safely in thought alone, the simple familiarity of Earth can feel like the rarest thing of all, a soft clearing in a universe of extremes. And yet, if we let our gaze drift just a little farther, we find that danger and strangeness are not confined to planets alone. Beyond these scorched and battered worlds, the universe keeps unfolding stranger things. Some objects hardly shine at all in ordinary light, slipping past our eyes and even our finest visible light telescopes. They reveal themselves only when we listen in other ways, especially at radio wavelengths, where space begins to sound less like a silent void and more like a distant, mechanical ticking. Among these hidden beacons are pulsars, neutron stars left behind after massive suns explode, tiny, heavy, and spinning at unbelievable speeds, keeping time in the dark with their relentless, whispering pulses. A neutron star is what you get when a star's core collapses so tightly that atoms themselves are crushed. Protons and electrons are squeezed together into neutrons, and almost all of the star's remaining mass is packed into a sphere only about 20 kilometers across. Imagine taking something more massive than our sun and folding it down until it would fit inside a large city. The result is so dense that a teaspoon of its matter would outweigh mountains. Some of these neutron stars spin hundreds or even thousands of times each minute, spraying beams of radiation out from their magnetic poles like cosmic lighthouses. When one of those beams happens to sweep across Earth, we detect a regular pulse click, 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 so steady that it can rival the precision of atomic clocks. Because the timing is so exact, any small disturbance in the path from pulsar to Earth stands out like a tiny hitch in a song. If another object passes in front or tugs on the pulsar with its gravity, the rhythm shifts just enough for careful instruments to notice. This is how some of the most unexpected planets have been found, not by their light, but by the way they make a distant, cosmic heartbeat stutter. One such pulsar lies roughly 4,000 light-years away, a compact star spinning so fast that it completes on the order of 10,000 rotations every minute. Its diameter is only around 20 kilometers, yet its mass is about 1.5 times that of the Sun, crammed into that tiny space. As it spins, it sends out powerful pulses of electromagnetic radiation in tight beams. Anything close to it is bathed not in gentle warmth, but in harsh, high-energy waves that would strip atmospheres and batter surfaces in a constant, invisible storm. Around this extreme object, incredibly, a planet orbits. This world circles the pulsar so tightly that its year lasts barely 2 hours. The distance between the planet and the neutron star is smaller than the radius of our sun, only a few 100,000 kilometers. That means the planet is held in a fierce gravitational grip, locked into a path that whips it around again and again through the pulsar's relentless beams. There is no true day or night here, just an endless strobing of deadly radiation. Despite its hostile environment, the planet itself is a fascinating thing to imagine. Its mass is roughly comparable to that of Jupiter, hundreds of times Earth's, yet its radius is only about 4 Earth diameters. Pack that much material into such a compact size, and you get an average density of around 20 times that of water. far higher than most substances we handle in everyday life. Gravity at its surface would be about 20 times stronger than on Earth. If you could somehow stand there without being torn apart by radiation, you would feel your body pressed down so hard that even the strongest bones and muscles would not be enough to lift you. The leading idea is that this strange world is made mostly of crystallized carbon under immense pressure, perhaps with a little oxygen mixed into its outer layers and bound into chemical compounds. Under those conditions, carbon can form a solid lattice that is, in essence, a gigantic diamond. The thought of an entire planet made largely of diamond sounds like something out of a story, but it follows naturally from the physics of dense matter and the remnants of old stars. It is beauty in a form we can never touch, embedded in one of the most lethal environments imaginable. It is very unlikely that such a planet survived unchanged from the time before the pulsar existed. A full supernova explosion would almost certainly have destroyed or flung away any original worlds. Instead, astronomers think this object probably formed later, from material left over after the star's violent death. One possibility is that it is the leftover core of a former white dwarf companion, shredded and stripped until only its densest heart remained in orbit. That blurs the line between what we call a planet and what we call a star fragment, making classification tricky. Whatever label we settle on, this diamond-like world remains one of the most exotic and hostile places hidden in the dark. Not all dangers in space come from compact remnants. Some are written on a much larger canvas, in stars that are nearing the end of their lives and swelling to enormous sizes. About 650 light-years away, in the direction of the constellation Leo, lies a star known as IRC plus 10216, or CW Leonis. It is a red giant in a very advanced stage, bloated and cool on the outside, but still burning fiercely within. At the peak of its expansion, its radius can reach more than 500 times that of the Sunday. To picture that, imagine placing CW Leonis where our Sun is now. Its outer layers would stretch out well past the orbits of Mercury, Venus, and Earth, swallowing them entirely, and likely reaching beyond Mars, brushing the inner edge of the asteroid belt. Planets that are now solid and distinct worlds would be moving through the star's outer atmosphere, their paths cutting through thin but scorching gas. Even though the star's surface temperature is only around 2,300 Kelvin, cooler than the Sun by comparison, its sheer size means it radiates thousands of times more energy. The mass of CW Leonis is not enormous by stellar standards, somewhere around 1.5 to a few times the mass of the Sunday in its youth. It is thought to have been a hot blue-white star, more massive and luminous than our own. Over billions of years, it burned through much of its hydrogen fuel in the core, fusing it into helium. Eventually, that helium collected into a dense, hot center, and the remaining hydrogen moved outward, burning in shells around it. This shift in structure set the stage for the star to swell. As the internal balance of pressure and gravity changed, the outer layers expanded greatly and became more rarefied. The star's color gradually shifted toward red, and its outer atmosphere grew unstable, prone to ripples and pulses. Deep inside, however, temperatures and pressures continued to climb. At a certain point, the helium in the core reached conditions where it could begin to fuse into heavier elements, mainly carbon. When that process starts suddenly, it can trigger what astronomers call a helium flash, a rapid, complex reaction that reorganizes the star's interior. During such changes, the core heats intensely, while the outer layers may cool and dim, CW Leonis is rich in carbon now, the product of those helium-burning reactions. But its mass is not quite high enough to push the chain of fusion much further. It cannot easily move on to fusing carbon into still heavier elements in a steady, sustained way. Instead, the burning becomes unstable, turning on and off in pulses. The star swells and contracts in slow cycles, each one accompanied by changes in brightness. For CW Leonis, this pulsation follows a rhythm of roughly 650 days. Over that time, its luminosity rises and falls from about 6,000 times the sun's output at its faintest to over 11,000 times the sun's at its brightest. When it expands, its outer layers grow cooler and darker, even as its interior roars more fiercely. When it contracts, those outer layers fall inward, heat increases, and the glow intensifies again. Seen from afar, the star's light waxes and wanes like a slow, deep breath. These pulses do more than change the star's appearance. With each cycle, some of the outer material becomes gravity's victim. The upper layers, already thin and unstable, can lose their grip and drift away into space. Carbon and oxygen atoms, along with other elements, are carried outward in a stellar wind. Around CW Leonis, this process has built up a thick envelope of gas and dust, a nebula made of the star's own shed skin. Estimates suggest that CW Leonis is losing mass at an astonishing rate, shedding many trillions of tons of material every year. Grain by grain, molecule by molecule, the star is enriching the space around it with carbon-rich dust that may one day become part of new clouds, new stars, new planets. From a safe distance, that seems gentle and beautiful, like a slow snowfall of ash. Up close, it would be a fierce, hot outflow, a storm of particles driven by radiation and heat. Stars like CW Leonis remind us that even the most stable lights in our sky are temporary. They grow, change, and eventually let go of their outer layers, sometimes quietly and sometimes violently. The planets that circle them can be swallowed, scorched, dragged inward, or left adrift in the aftermath. The diamond whirled around a pulsar, the giant red star wrapped in its own carbon fog, these are all parts of the same long story of birth, transformation, and loss. Thinking about them from the comfort of our own small orbit, there is a kind of quiet comfort in knowing that we are watching from far away, reading only the echoes. The lethal beams of pulsars, the crushing gravities and swollen stellar envelopes cannot touch us here. They arrive instead as faint signals in radio dishes and soft patterns in starlight, clues that let us trace the wild variety of ways the universe makes and unmakes its worlds. In the dim stillness of night, those clues become stories, and those stories gently deepen the feeling that, for all its dangers, the cosmos is a place we are allowed to understand, especially when we lean in on one star and watch its long unraveling up close. The material surrounding CW Leonis doesn't drift away quickly. Instead, everything the star has breathed out over tens of thousands of years has collected around it like a thick, glowing shroud, a visible record of that slow unraveling. This circumstellar cloud is older than entire human civilizations, at least 69,000 years, and it contains roughly 1.5 times the mass of our sun, suspended in a loose, expanding shell. Its size is even harder to grasp. It stretches outward for tens of thousands of astronomical units, reaching far beyond the region where planets would normally roam. out into the quiet outskirts of the local interstellar neighborhood. Within that vastness, the matter is not evenly spread. Some regions are dense and swollen, like pockets of air trapped under fabric. Others are hollowed into delicate hollows and partial rings. Half-arcs curl like the trails left by slow fireworks. These shapes likely form as stellar winds push outward in uneven gusts, twisted by the shifting magnetic fields of an aging, unstable star. Even from an immense distance, the cloud looks alive in its own slow way, constantly reshaped by forces we can only observe in soft traces of light. If we break that light apart into its component colors, a detailed chemical story begins to appear. The cloud holds at least 70 different molecular species, simple ones like water vapor, carbon dioxide, and ammonia, but also more complex carbon-bearing molecules, silicates, and compounds that include elements stretching far up the periodic table: iron, silicon, sulfur, aluminum. They drift in the fog, mingling with carbon grains and organic fragments. In this dusty cocoon, the universe is quietly inventorying the ingredients for future worlds, mixing and recycling matter the star can no longer hold. CW Leonis may once have had planets of its own, circling comfortably when the star was young and blue-white. If they ever existed, they almost certainly vanished early, swallowed by the expanding star as it entered its red giant phase. For decades, astronomers have searched for leftover motion, small, rhythmic wobbles in the star's position that might hint at surviving companions. What they've found instead are only the faintest irregularities, slight shifts in the star's motion noted in the 1,990 seconds, and more recent changes in the movement of gas and dust near it. These subtle disturbances have led to a quiet speculation. Perhaps CW Leonis still has a companion, a small red dwarf orbiting at a respectful distance, tugging gently on the giant's mass and churning the surrounding envelope. If such a companion exists, it would complete a long orbit, roughly once every century, but looking for it directly is almost impossible. The bright, dusty cloud around the star scatters and diffuses any nearby light, masking small, faint objects entirely. Even a star only slightly smaller than the sun could sit inside that haze and never reveal itself clearly. Among all the oddities surrounding CW Leonis, water is one of the most surprising. Near a red giant's surface, conditions are typically too hot, too unstable, and too oxygen-poor for water vapor to form naturally. So when astronomers first detected signs of water, they assumed the star had swallowed icy comets as it grew. That explanation made sense until more detailed observations arrived. In 2009, measurements showed spectral signatures of water at temperatures near 1,000 Kelvin, far hotter than cometary ices could produce. The water was being made in place, inside the star's own extended atmosphere. But how? By traditional models, nearly all free oxygen in a carbon-rich red giant should be bound up tightly in carbon monoxide. That leaves almost none available to create water. To explain the new evidence, researchers proposed a more dramatic process: intense ultraviolet radiation breaking apart carbon monoxide and silicate molecules, releasing oxygen atoms that could then join with hydrogen to create water vapor. Yet this raised another puzzle. Where would such strong ultraviolet light come from? The outer layers of a red giant are usually thick enough to block almost all high-energy photons from the interior. A newer idea suggests that CW Leonis may not have an entirely smooth surface. Unstable stars sometimes develop temporary gaps or thin spots in their outer layers, brief, low-density corridors where radiation can escape more freely. Through these openings, ultraviolet light could leak outward, strike nearby molecules, break them apart, and trigger the chemical chains that create water. These breaches would not last long, and they would be nearly impossible to see directly. But the overheated water they produce glows in unmistakable ways, revealing their presence indirectly. Even with all those processes working together, water is only a tiny fraction of the star's total mass. The amount sounds enormous, billions upon billions of tons of vapor, but it accounts for no more than a billionth of the star's full weight. Still, its presence is a reminder that the dying breath of a star is not empty or simple. It is rich, reactive, and full of complexity, a place where molecules form and dissolve in a slow, flickering dance. According to what we know about stellar evolution, CW Leonis is deep into its aging phase. In another 10 to 30,000 years, a moment in cosmic time, it will exhaust the last of the fuel it burns in its core. When that happens, its outer layers will no longer be held upward by internal pressure. They will drift outward in a final, powerful expansion, peeling away into space and brightening the surrounding nebula. What remains afterward will be its compact, blazing hot core, a white dwarf. At first, this remnant will be indescribably hot, reaching temperatures of millions of degrees, but it won't have any new source of energy to sustain its glow. Over billions of years, it will gradually cool, dimming from white to red to ember-like darkness. Far in the future, long after humanity, long after Earth itself, it will fade into a black dwarf, a cold, quiet object with no light of its own, drifting silently in the dark. Yet before that long cooling begins, the moment of transformation will be violent and creative. When a star's outer layers are ejected, the shock waves and intense heat produce elements that cannot form inside a stable star: gold, uranium, lead, and other heavy atoms. These newly forged elements drift outward, mixing with interstellar gas. Over millions of years, they may settle into clouds that form new stars and planets. Radioactive elements buried in young planets slowly release heat as they decay, warming their interiors, powering volcanic activity, melting subsurface ice, and feeding chemical reactions that could, under the right circumstances, support life. Destruction, in this way, becomes the seed of new beginnings. All of this starts with the simple physics of fusion. Inside stars, conditions are so extreme that hydrogen nuclei normally content to drift apart are pushed close enough to fuse. When two hydrogen atoms join to form helium, they release energy, along with an electron and tiny ghost-like particles called neutrinos. That energy is what lights up the universe. As stars get hotter, other light elements, like lithium, carbon, and oxygen, also participate in fusion cycles, forging heavier atoms such as sulfur, magnesium, and phosphorus. These reactions require far more energy because heavier nuclei repel one another more strongly. Only the most massive stars can sustain such processes for long. When a star similar to our Sun consumes most of its hydrogen, it swells into a red giant, cools at the surface, and burns helium in its core to create carbon and oxygen. Eventually, it becomes unstable. With no steady fuel left, it sheds its outer layers, leaving a white dwarf behind. But stars significantly heavier take a different path. When their hydrogen is gone, they can continue to produce energy through the fusion of heavier elements. As the outer layers are blown away by powerful stellar winds, the hot inner core becomes exposed. These stripped-down, luminous cores are known as Wolf-Rayet stars. Wolf-Rayet stars were first recognized in 1867 by French astronomers Charles Wolf and Georges Rayet, who noticed unusually strong emission lines of heavy elements in their spectra. These stars contain little hydrogen, having already discarded it, and instead show bright signs of carbon, nitrogen, helium, and sometimes oxygen. They are rare and short-lived, with only a few hundred identified in the Milky Way, even accounting for those too distant or obscured to detect. Their total number is unlikely to exceed a couple of thousand. Depending on which elements dominate their spectra, Wolf-Rayet stars are grouped into three broad families: those rich in nitrogen, those rich in carbon, and those marked by strong oxygen emissions. Each type represents a slightly different chapter in the same story: a massive star nearing the end, its outer layers peeled away, revealing the deeper, hotter regions that are usually hidden. Surrounding nebulae, diamond-like planets near pulsars, white dwarfs cooling through slow eons, and the fierce glow of Wolf-Rayet stars all fit into a single, continuous pattern. The universe is always shifting. Matter is melted, crushed, blown apart, radiated outward, and then gathered again in new forms. What looks like ruin from a distance, the death of a star, the shattering of a world, often becomes the quiet foundation for something new. And in that endless cycle, in all the violence and creation woven together, there is a soft reminder, tucked between the stars, that for a brief moment, on a small and gentle world, we get to witness it from far away, safe in the calm of our own orbit. Among Wolf-Rayet stars, astronomers sort them into different families based on which heavy elements stand out most in their light: nitrogen, carbon, or oxygen. Within each family, there are more subtle types, like branches of the same tree. The hottest known star in the observed universe, at least with our current instruments, belongs to the oxygen-rich branch. It carries the name WR-102, a short label for an object that pushes almost everything about heat and brightness to an extreme. WR-102 first slipped into our awareness in 1971. At the time, it was thought to be the visible companion of an X-ray source called GX3+1, a kind of optical counterpart to a mysterious high-energy signal. Later, with more careful observations, astronomers realized they were looking at two completely different objects in the same patch of sky. One was the original X-ray source. The other, this tiny, furious point of light, turned out to be something else entirely: an extraordinarily hot, oxygen-rich Wolf-Rayet star. When its light was broken apart into a spectrum, the lines of oxygen leapt out, unusually bright and strong. Those lines were the star's signature, revealing the chemistry of its outer layers. In 1982, WR-102 and 4, similarly intense stars, became the first known members of a new spectral class, oxygen sequence, Wolf-Rayet stars. They were so distinct that they had to be given their own category, a new corner of the Stellar Family album. Measurements of WR-102's light tell us that its surface temperature exceeds 210,000 Kelvin. That is roughly 36 times hotter than the sun's surface. At such temperatures, atoms are stripped of many of their electrons, and matter behaves more like a glowing plasma than anything we might imagine as gas. This extreme heat makes the star astonishingly luminous, estimated at well over 380,000 times the brightness of our Sunday. If WR102 were somehow placed where the Sun is now, its light would overwhelm the sky so completely that night, as we know it, simply would not exist. Yet for all that brilliance, WR102 is invisible to the naked eye. It sits about 10,000 light-years away from us, in the direction of the constellation Sagittarius, buried behind clouds of dust and gas that dim its light along the way. To us, it's revealed only through sensitive detectors and careful analysis, a distant ember we can measure but never see directly with unassisted eyes. The fact that something so bright can still be hidden feels like a quiet reminder of how much the galaxy can soften and disguise even its most intense fires. In its current state, WR102 belongs to an especially rare subset of Wolf-Rayet stars called WO stars. These are stars whose outer layers are dominated by oxygen, with almost no hydrogen left at all. Their energy no longer comes from fusing hydrogen into helium the way our Sun does. Instead, they draw power from the fusion of heavier atomic cores, neon, carbon, oxygen, deep in their interiors. Only 9 stars of this HO type have been identified so far, with 4 in our Milky Way and the rest in other galaxies. They are like the final, concentrated notes at the end of a long stellar song. Their rarity is no accident. First, Wolf-Rayet stars themselves are uncommon. Only the most massive stars, those born with at least around 40 times the Sun's mass, are likely to pass through a Wolf-Rayet stage. Second, the WO phase is a brief final act, lasting perhaps only 1,000 to 10,000 years. On human timescales, that sounds long. On cosmic scales, it's barely a blink. To catch a star precisely in this stage is like glancing at a tree and seeing the exact moment a single leaf lets go. WR102 is relatively modest in size, at least when measured by radius. Its outer layers extend to only about 58% of the Sun's radius, making it physically smaller in volume. But that compact shell contains a tremendous amount of mass, somewhere between 15 and 18 times the mass of our Sunday. When it was born, WR102 may have been even heavier, with an original mass, perhaps in the range of 40 to 60 solar masses. Over time, intense heat and ferocious nuclear reactions have driven powerful winds that strip the star of its outer layers, peeling it down toward its core. Those stellar winds are astonishingly strong. Particles are launched outward at speeds exceeding 5,000 kilometers per second, blowing past what we think of as the escape velocity of many stars. At that rate, WR102 loses roughly the equivalent of Earth's mass in just a few months. Over a span of 10,000 years, it can shed a mass similar to that of the Sunday. The star is, in a sense, burning itself away in slow motion, sacrificing its outer layers to space as it races through the last stages of its life. No planets circle WR102, at least none that our current observations can detect. Even if they had formed once, they would have struggled to survive the intense radiation and roaring winds. Instead, the star is wrapped in a diffuse envelope of gas, sculpted by ultraviolet light and the force of its own outflow. The gas becomes ionized, its atoms stripped of electrons, glowing and forming loops, knots, and arches that curl outward from the star. Some astronomers think this cloud is the leftover of the original hydrogen-rich outer layers, now blown away and illuminated from within. Others suggest it may be built continuously by the current wind, a living shell formed from material still being shed. WR-102 is not alone in its fierce heat. Several other stars, objects like WR-142, WR3, WR93b, and the central star of the Butterfly, or Bug Nebula, NGC 6302, reach surface temperatures of around 200,000 Kelvin. Some white dwarfs, freshly revealed after a star's outer layers are thrown off, can also approach these staggering surface temperatures. But even these intense objects are outshone in terms of pure thermal extremes by a different family of remnants, neutron stars. When a massive star collapses in a supernova, its core can be crushed into a neutron star. In their first moments of existence, newborn neutron stars can reach temperatures of around 100 billion Kelvin. Almost immediately, they begin to cool, mainly by streaming out neutrinos, tiny particles that pass through nearly everything. Even after this rapid cooling, their surfaces remain incredibly hot, staying at hundreds of thousands of Kelvin or more for a very long time. Their cores, hidden from direct view, are hotter still, packed with matter in states we can only guess at. Yet even neutron stars are not the final word in temperature. To talk about the ultimate limit, physicists reach back not to any single object, but to the earliest imaginable moment, the birth of the universe. In the framework of modern cosmology, the temperature of the universe right at the beginning of the Big Bang is estimated to have reached around 1.4 times 10 to the power of 32 Kelvin. This value, called the Planck temperature, is so extreme that the physical laws we rely on start to lose their meaning. Beyond that point, our current theories simply fail. We do not yet have a language that can accurately describe what matter or energy would be like. It is less a number we expect to see in reality, and more a boundary line on the map, drawn at the edge of understanding. Against that backdrop, the heat of WR-102 feels like both an unimaginable furnace and a modest ember. It is blazing enough to strip atoms, drive hurricane-like winds of plasma, and shine hundreds of thousands of times brighter than the sunday. And yet, when we set its temperature alongside the theoretical extremes of the early universe, it becomes one more step on a long scale that stretches far beyond our direct experience. From what we know about stellar evolution, WR-102 is firmly in its late autumn. Unlike stars similar to the Sun, which puff up into red giants in their final acts, massive Wolf-Rayet stars stay compact. Their strong gravity keeps their material pulled inward, forming dense, hot spheres rather than swollen envelopes. Even so, the relentless mass loss from powerful winds gradually erodes the delicate balance that holds them stable. At some point, the star will no longer be able to support its own weight. Current estimates suggest that WR-102 could be on the verge of a supernova within the next 1,500 years. Because light takes 10,000 years to travel from the star to us, the explosion may already have happened in reality, its shock waves rushing outward through space, still thousands of years away from appearing in our sky. When it does arrive, observers on Earth would see a sudden, brilliant star blossom for a time in the direction of Sagittarius, outshining many of the familiar points around it. Such a supernova, would almost certainly be accompanied by intense bursts of high-energy radiation, including gamma rays. But at a distance of 10,000 light-years, our planet is far enough away that these emissions would be safely diluted by the time they reached us. WR-102 is dangerous in the sense of its power, but not in the sense of any direct threat. Its drama plays out at a safe remove for us to watch as quiet witnesses. Inside the star, heavy elements, up to iron, have already formed over its lifetime. When the core finally collapses, the energies and densities reached in the explosion will trigger rapid proton and neutron capture processes, chains of reactions that forge elements even heavier than iron, including those beyond uranium. These transuranium elements may exist only briefly before they decay, but in doing so, they help feed the complex chemistry that will belong to the next generations of stars and planets. Where WR-102 once was, a neutron star will likely remain, a tiny, incredibly dense ember, spinning in the quiet aftermath. Around that remnant, the outer layers of the star will be blown outward into a new nebula, rich in heavy elements, cooling slowly as it expands. Over millions and billions of years, this cloud will drift and mix with other material, maybe joining with gas from distant regions to form fresh molecular clouds. One day, in some far-off era, that enriched gas might collapse again, giving rise to new stars, new planets, and worlds that will never know they carry atoms forged in the heart of WR-102. As we follow this chain from the fierce heat of Wolf-Rayet stars to the even more extreme newborn neutron stars, and back to the unimaginably hot beginning of the universe, it becomes clear that there are limits to what we can see directly. Some things are so bright that they burn out quickly. Others are so dense that they hide themselves from view. And there are places out in the dark where the difficulty is not that something shines too dimly or even too fiercely, but that it does not shine at all. Objects that swallow light instead of emitting it pose their own quiet challenge. If they take in every ray that falls on them, how can we ever be sure they are there? That question leads us into another kind of abyss, where gravity becomes so strong that even light cannot escape. When we talk about things that swallow light, it's easy to imagine that the universe must be crowded with them, lurking behind every star. In reality, even the darkest objects are surprisingly rare. Black holes are difficult to find because they emit no light of their own. But when astronomers model the Milky Way and fold in everything we know about how stars live and die, they estimate that our galaxy may host around 100 million of them. That sounds enormous, until you set it next to the total number of stars, roughly 200 to 400 billion. Then the picture softens. In the vast sweep of the Milky Way, black holes are more like scattered deep wells than an endless field of traps. To form one of these wells, a star has to start life with a lot of weight, not just a little heavier than the sun, but many times more massive. The current understanding is that a star needs at least 18 to 20 times the sun's mass, and often more, for its death to lead to a true black hole. When such a giant runs out of fuel in its core, the balance between outward pressure and inward gravity collapses. The outer layers explode outward as a supernova, while the inner core is compressed so violently that not even atomic nuclei can resist. Matter is squeezed into a region so dense that its escape speed exceeds the speed of light. Physics tells us that around such an object, there is a boundary, a kind of invisible shell called the Schwarzschild radius. Inside that radius, no path leads outward. Light itself, which usually moves along the swiftest possible routes through space-time, finds that every direction curves inward. What used to be a star becomes an object whose internal structure we cannot describe with the familiar tools of everyday physics. We can define its mass, its spin, its electric charge, and we can feel its gravity. But what lies inside that boundary is still hidden behind a curtain of theory and speculation. One of the closest known black holes to Earth carries the catalog name A62000 and is also sometimes called V616 Monocerotis, after the constellation where it resides. It lies about 3,300 light-years away, a neighbor by galactic standards, and it does not float alone. It's part of a binary system, paired with a small orange star, roughly half the Sun's mass. The two objects circle a shared center of gravity, locked together in an intimate orbital dance that repeats every 7 3/4 hours. We never see the black hole itself, of course. What we do see is the effect its gravity has on its companion. The orange star is stretched, slightly out of shape, pulled toward the invisible mass, like a drop of water drawn toward a drain. Gas from its outer layers spills over, funneled by gravity into a spiraling stream that falls inward. As this gas gathers into a thin, bright disk around the black hole, it heats up from friction and compression, glowing in X-rays and visible light. It is that shining accretion disk, not the black hole, that our telescopes detect. The region around V616 Mon is not empty. There are dozens of stars nearby, some of which almost certainly host planets of their own. In the deep future, one of these neighbors could drift too close, feeling a growing tug from the black hole's gravity. If its path carries it within a certain critical distance, the balance of its orbit could be broken, and the star might be captured into a new, tighter trajectory. Over time, it could be stripped the way the current companion is being stripped, its outer layers fed into a fresh, hot disk that flares briefly against the darkness. How a black hole and its companions interact depends gently but firmly on three things: their masses, their distances, and their relative motions. The more massive the black hole and the closer the other object comes, the stronger the tidal forces it feels. Tidal forces are simply the difference in gravity between one side of an object and the other. When those differences are extreme, a star or planet can be stretched along one direction and squeezed along another, distorted like a lump of dough being pulled apart. If the pull grows too strong, those tides can open channels that funnel gas outward or even tear the object into streams and clouds that wrap themselves around the black hole before disappearing into the disk. Despite their ominous reputation, black holes do not behave like cosmic vacuum cleaners that indiscriminately suck in everything nearby. From the standpoint of gravity, they act much like any other object of the same mass. If our sun were suddenly replaced by a black hole with exactly the same mass, Earth's orbit would barely change. We would keep circling in almost the same path, just bathed in darkness instead of sunlight. Stable orbits can exist around black holes, just as they do around stars. The danger only rises sharply when something ventures too close. Because of this, there is no reason in principle why a black hole could not have planets. They might move in quiet, regular paths, unaware in any direct way that their central mass is not a glowing star, but a lightless sphere. In some scenarios, new planets could form after the supernova that created the black hole. The explosion leaves behind a cloud of gas and dust, a nebula that can, over time, cool and clump. Under the pull of gravity, those clumps collide, stick together, and slowly grow into larger bodies, planetesimals, asteroids, moons, and eventually full-fledged planets. The black hole's accretion disk, if still active, might provide warmth and energy, especially in its inner regions, potentially melting ice and driving chemistry on nearby worlds. In other cases, planets might arrive as survivors. When a massive star dies and collapses, it can disturb or destroy its original planetary system, but not all objects are necessarily lost. Some may be flung away as wanderers, and others may settle into new orbits around the remnant. A gas giant might be stripped of most of its hydrogen, leaving behind a dense, rocky, or icy core. What was once a Jupiter-like world could become a smaller, compact planet. An icy giant might see its frozen layers warmed, pulling subsurface oceans closer to the surface. The surfaces of such planets would be altered dramatically, yet they could still find a kind of fragile stability around their new, dark host. There is also the possibility that rogue planets and drifting debris worlds kicked out of other systems. Lonely asteroids traveling between stars could be captured by a black hole's gravity. If their incoming speed and direction are just right, they might settle into long, looping paths, trading isolation in interstellar space for a place in a new and peculiar family. So far, we have not yet observed a planetary system clearly and unambiguously bound to a black hole, but there is no physical law that forbids it. In a galaxy as large and as old as ours, it would be surprising if such systems never formed at all. Of course, not every orbit ends well. If a planet circles too close to a massive black hole, other forces besides gravity's gentle pull start to matter. The disk of infalling gas around an active black hole can be intensely hot, emitting radiation and blowing out winds of particles. A planet embedded too deeply in that environment could have its atmosphere stripped away grain by grain, like sand blown off a dune. Friction with the surrounding gas could erode its orbit, causing it to spiral inward, slowly but surely. Closer still, tidal forces grow overwhelming. Rock, metal, and ice can all be stretched beyond their ability to hold together. The planet may be pulled apart into streams of debris, forming a temporary, luminous ring as the fragments heat up in the disk. Over time, even those fragments are ground down, melted, and blended into the swirling gas, eventually crossing the event horizon and becoming part of the black hole's mass. From the outside, we would see a flare, a brief brightening of the disk, and then a quiet return to darkness. Across the universe, black holes themselves come in different scales. One major group lives at the hearts of galaxies. These are the supermassive black holes, with masses ranging from millions to billions of suns. In the crowded centers of spiral galaxies like the Milky Way, stars are packed closely together, and gas clouds are dense. Massive stars form, shine briefly with enormous brightness, and die. Their remnants, black holes and neutron stars, can merge and grow, feeding on gas funneled toward the center. Over long stretches of time, this process can build a central black hole of truly staggering size. Around some of these giants, the inflow of matter is so intense that their accretion disks outshine entire galaxies. Gas spirals inward, heats to extreme temperatures, and blasts out radiation across the spectrum, from radio waves to X-rays. From billions of light years away, such active galactic nuclei can appear as tiny, brilliant points, quasars and blazars, beacons so bright that they pierce the fog of intergalactic space. At their core sits a black hole, utterly dark, wrapped in light, created by everything falling toward it. So we move from rare stellar mass black holes quietly orbiting with small companions to vast central monsters sculpting the evolution of whole galaxies. Between them lie other kinds yet to be fully understood. But whether small or enormous, isolated or surrounded by blazing disks, each black hole is a place where our ordinary intuitions falter. Gravity curves so sharply that even light cannot climb out. Time itself behaves strangely near the edge, and in their presence, the familiar categories of surface and inside start to slip away. From the calm of a quiet night, all of this is safely distant. The nearest known black holes are too far to influence us. The central giant in our own galaxy sits tens of thousands of light years away. Their violence arrives at Earth only as faint whispers in radio waves, subtle shifts in starlight, and the ripples of gravitational waves caught by sensitive detectors. Listening to those whispers, we learn how the universe handles its most intense extremes, and we carry that knowledge back to our gentle corner, where starlight still reaches the ground and the sky remains, for now, reassuringly bright. When a supermassive black hole at the heart of a galaxy feeds very actively, the light from its accretion disk can drown out the glow of billions of surrounding stars. From far away, the galaxy itself can become almost invisible, while its bright, compact center blazes like a distant beacon. Objects like that are called quasars, quasi-stellar radio sources. Even when their host galaxies are too faint or too small to make out clearly, these brilliant cores tell us that something very heavy and very hungry is sitting at the center, quietly bending space and time. Not every black hole is so dramatic. The second broad family is far more common, but also more subtle. These are stellar mass black holes, born when very massive stars collapse at the end of their lives. At first, their masses are only a few times that of the Sun, maybe 10 or 20 times at most. Over long spans of time, though, some of them grow. By feeding on nearby gas, swallowing passing clouds, or slowly stripping material from companion stars, they can increase their mass. When several stellar mass black holes eventually merge, drawn together over millions of years by gravity, they can build up into what we call intermediate mass black holes, stepping stones between the stellar and the truly gigantic. Each time two black holes join, the union sends out ripples through space-time, gravitational waves, spreading outward like the faintest possible vibrations across a cosmic pond. These waves pass through everything, stretching and squeezing distances by amounts so small they are almost unthinkable. On Earth, we can only detect them with instruments that look for changes far smaller than the width of an atom. And yet, by catching those tiny shivers, we can hear the final moments of black holes spiraling into each other, far beyond the reach of any light. The third category of black holes belongs, for now, mostly to theory. These are primordial black holes, thought to be possible products of the universe's earliest moments. In the first fractions of a second after the Big Bang, matter and energy were packed together in ways that allowed for tiny ripples in density regions, slightly heavier or lighter than others. Under the right conditions, some of those overdense pockets could have collapsed on themselves, forming black holes much smaller than those made by stars. They might have ranged from the mass of mountains to that of asteroids, or even less. If such primordial black holes were born, their lifetimes would depend strongly on their mass. According to theoretical work on quantum effects near the event horizon, black holes slowly lose energy over time through what is known as Hawking radiation. The smaller the black hole, the faster this evaporation process. In the final moments of their lives, tiny black holes would release their remaining energy in a brief, powerful burst of radiation, like a sudden flare in the dark. Calculations suggest that primordial black holes with masses around 1 trillion kilograms, if they ever existed, would be reaching the ends of their lives around now. But despite careful searches, no unmistakable signature of such an evaporation event has yet been seen. There is also the idea of quantum black holes, microscopic objects that might form in collisions between particles at unimaginably high energies. In principle, if two particles slammed together with enough energy in a very small region, they could briefly curve space-time sharply enough to trap themselves in a tiny event horizon. Such black holes would be incredibly short-lived, evaporating almost immediately in a flash of particles and radiation. The energies required are far beyond what we can reach in any laboratory. Even if they have been created in rare, natural cosmic ray collisions, their lifetimes would be so short that, with our current instruments, they are effectively ghost predictions on paper rather than observed realities. All of this makes black holes difficult companions for observers. They are dark, compact, and often far away. Detecting them is a matter of looking not at the object itself, but at what it does to its surroundings. Sometimes, we are lucky enough to find a star traveling in a way that makes no sense unless something invisible and massive is close by. The star's orbit may be too tight, too fast, or oddly stretched, pointing to the presence of an unseen partner. By tracking the star's motion carefully, astronomers can estimate the mass of the hidden object and determine whether it is too heavy to be a neutron star or any other known type of remnant. In those cases, a black hole becomes the most reasonable explanation. In other situations, the giveaway is light from an accretion disk. Gas spiraling toward a black hole heats up as it rubs against itself and falls inward, glowing in X-rays and other wavelengths. The spectra of these disks, how their light is spread across energy, can have characteristic shapes that set them apart from ordinary stars or galaxies. In a few special cases, our instruments can even resolve the structure of the disk itself. We see a bright ring with a shadowed center, not because the black hole has a physical surface, but because light from the far side is bent and warped in ways our eyes are still learning to interpret. There is another, more delicate way to sense a black hole's presence: gravitational microlensing. If a massive object passes exactly between us and a distant star, its gravity can act like a lens, bending and focusing the star's light. The star appears to brighten and then dim again in a very specific pattern. In most microlensing events, the lens is a faint star or brown dwarf, but occasionally the mass could be a black hole. To catch such an alignment, we need several layers of luck: the right object in the right place, passing in front of the right background star at just the right time. It is a reminder that much of astronomy is patient listening, waiting for rare moments when the universe lines things up for us. From this world of hidden masses and bent light, it can feel grounding to return to a more familiar scale. Our planet is, after all, just a small, solid fragment moving in a nearly circular path around the sun at a distance of about 1 astronomical unit, roughly 150 million kilometers. It has been following this path for billions of years, looping tirelessly through space. But even our own solar system is much larger than the orbit of Earth alone. Far beyond the planets, icy bodies and distant comets are thought to form a diffuse shell called the Oort cloud, stretching perhaps out to 100,000 astronomical units from the Sunday. Past that hazy border, the sun's gravitational influence weakens to a whisper, and the interstellar medium takes over. Out there, space is so empty that, on average, there may be only a single hydrogen atom in each cubic centimeter. In our part of the galaxy, the nearest stars lie a few light years away from us. A photon leaving the sun could travel all the way to Proxima Centauri, our closest stellar neighbor, without ever colliding with a single particle of matter. The void between stars is not perfectly empty, but it is as close to nothing as nature allows on such scales. This near-nothingness permeates the Milky Way, threading between its spiral arms, separating stars, planets, black holes, white dwarfs, neutron stars, and glowing nebulae. If you drift outward, beyond the galaxy's disk, the emptiness deepens further. Between us and the Andromeda Galaxy, for example, lie about 2.5 million light-years of space so rarefied that, in human terms, it might as well be pure absence. That gap is wide enough that 20 or more galaxies the size of the Milky Way could line up end to end within it, and yet almost no luminous matter fills it. Only a handful of lonely dwarf galaxies and thin wisps of gas cross that gulf. The Milky Way, Andromeda, the Triangulum Galaxy, and around 100 smaller satellites around them form a bound family called the Local Group. Gravity ties these galaxies together, guiding their motions as they orbit a shared center of mass over billions of years. The Local Group spans roughly 10 million light-years from edge to edge, a modest gathering by cosmic standards. It floats embedded in a larger, flattened structure of galaxies called the local sheet, a kind of thin, gravitationally knit slab. The local sheet stretches about 46 million light-years across and only around 5 million light-years thick, containing several hundred galaxies. It is as if our galactic neighborhood rests on a vast, invisible table, with most of its members confined to that plane. This sheet is, in turn, part of an even grander association known as the Virgo Supercluster, a sprawling collection of galaxy groups and clusters spread across tens of millions of light-years. Yet even here, structure is not uniform. Near the edge of the local sheet, the scenery changes in a quiet but dramatic way. Where we might expect more clusters and filaments of galaxies, we instead encounter a region largely empty of them, the local void. In a sense, the local sheet serves as one wall of this immense hollow in the cosmic web. Other superclusters, such as Perseus, Pisces, and Pavo Indus, help define additional boundaries. Within the void itself, a few thin, tenuous filaments of galaxies thread through, and wide passages connected to neighboring voids, like Sculptor and Hercules, creating a network of low-density regions. Because the universe is expanding and matter clumps together under its own gravity, the volumes of such voids tend to grow over time. The local void is no exception. Its current diameter is estimated to be around 150 million light-years, with its center at least 70 million light-years away from us. The nearest edge of this vast empty region lies surprisingly close, only about 3.2 million light-years away, closer, in fact, than many of the more distant members of our local group. From Earth's perspective, The local void covers a large swath of the night sky, perhaps around 40% of the visible dome. The bright band of the Milky Way's disk runs across this area, filled with stars, nebulae, and dark lanes of dust. That dense foreground partially hides the deeper emptiness beyond, like a curtain of fireflies in front of a dark field. But around the edges, where our galaxy's own stars thin out, the void's character becomes more apparent. There are simply fewer galaxies in those directions, fewer distant smudges of light. In the middle of that underpopulated region sits a small, graceful spiral galaxy called NGC 6503, discovered in the mid-19th century near the constellation Draco, just north of Hercules. It is sometimes described as the lonely little galaxy at the edge of the void. It is not truly alone, but it does occupy a place where neighbors are sparse. In deep images, its star-forming regions and clusters stand out in subtle colors: pale blues, soft reds, misty whites, set against a backdrop that holds far fewer distant galaxies than one might expect. Seen from here, NGC 6503 is a reminder that emptiness and structure coexist at every scale. Galaxies gather in groups, sheets, and clusters, but between them are volumes where almost nothing shines. Stars collapse into black holes that cannot be seen directly, surrounded by glowing disks. Beyond them lie spaces so empty that a photon can cross millions of light years, almost unimpeded. Between the densest fire and the deepest quiet, the universe holds both extremes, and somehow, in a thin middle ground, our small world has found room to orbit, to cool, and to wonder. If you could drift up close to NGC 6503 and look down at it from above, it would feel strangely familiar and yet quietly different. Its spiral arms curl gently around a faint central region, threaded with soft colors. Along the arms, bright red knots of glowing hydrogen trace out pockets of active star formation regions where gas has been heated and ionized by newborn, massive stars. Between them, small blue clouds and clusters shine where young, hot stars are still gathered close together. These are stellar nurseries, places where gravity is pulling gas into new suns, while radiation pushes back, shaping filaments and bubbles in slow motion. In the central area, the galaxy's heart is partly veiled by darker lanes of cooler gas and dust. From a distance, those obscuring clouds look almost brownish or smoky, like smudges on a painted disk. They block and scatter light from stars behind them, hiding some of the inner structure from view. Even so, we can trace the overall shape and size. NGC 6503 spans roughly 30,000 light-years from one side to the other, making it a bit smaller than the Milky Way, more like a compact, softly spinning island of stars suspended in the emptiness of the local void. This little galaxy sits about 17 million light-years from Earth, out by itself, in a region where there are relatively few neighbors. Despite that isolation, it's not drifting freely. The gentle pull of gravity from the Virgo supercluster, the sprawling collection of galaxy groups we belong to, is slowly drawing NGC 6503 toward the thicker part of the cosmic web. Measured along our line of sight, it approaches us at about 43 kilometers per second. That speed sounds fast, but on the scale of millions of light years, it is a quiet, patient motion, like a slow tide. As NGC 6503 eases closer to the denser parts of the local sheet, it is expected to encounter more intergalactic hydrogen, thin streams, and clouds of gas that lie between galaxies. Over billions of years, this material can be pulled into the galaxy's halo and disk, adding fresh fuel for star formation. Models suggest that, given enough time, the current population of young stars could increase significantly, perhaps even double. The galaxy, which now shines with a calm, steady light, may someday glow more intensely, lit up by new generations of stars born from the gas it gathers. The motion of NGC 6503 offers a quiet clue about how cosmic voids themselves came to be. The large-scale pattern of clusters, filaments, and hollows that we see today did not appear all at once. According to modern cosmology, the seeds were planted in the universe's first minutes, when matter and energy were still in a hot, chaotic mix. Tiny fluctuations in density, slightly heavier and lighter regions were imprinted in this early soup. Over time, the denser spots began to pull in more material under gravity, while the less dense regions gave up matter and became emptier. Those denser clumps grew into the first proto-galactic clouds, places where stars would eventually form, while the sparser regions stretched into voids. As billions of years passed, gravity amplified the contrast. Gas and dark matter continued to flow toward filaments and nodes, feeding clusters and superclusters of galaxies. The gaps between these structures, deprived of matter, became more and more rarefied. A pattern emerged, a kind of cosmic foam, with galaxies tracing out the walls and edges of vast, nearly empty chambers. Observations tell us that most galaxies we see, whether in busy filaments or in quiet voids, formed long ago, roughly 10 to 13 billion years in the past. Interestingly, there is no strong evidence that galaxies in voids are systematically younger or older than their counterparts in denser regions. They seem to share similar ages, pointing to a common early era of galaxy formation across the universe. This supports the idea that the large-scale structure was laid out early, and that voids and filaments have grown together from the same initial pattern. As the universe continues to expand, the spaces between clusters and superclusters grow wider, voids stretch, and the matter within filaments slowly drains further toward their densest nodes. In the distant future, the local void will likely become larger and even more underpopulated, while structures like the Virgo supercluster gradually loosen and fragment into smaller, more isolated groups. Right now, Virgo is an impressive association. Around 30,000 galaxies gathered in a region roughly 200 million light-years across. The total mass of the Virgo supercluster, when we include both visible matter and the dark matter inferred from its gravitational pull, is estimated to be on the order of a quadrillion times the Sun's mass, roughly equivalent to the combined mass of about 1,000 Milky Way-sized galaxies. Virgo itself does not float alone. It brushes up against other large arrangements. On some sides, it connects to the Centaurus supercluster and the Pavo-Indus supercluster, forming part of a larger web of galaxy concentrations. On another side, however, it faces something very different, a deep, relatively empty expanse known as the Taurus Void. The Taurus Void is one of the largest known cosmic voids. Studying it is challenging because much of it lies behind the plane of our own galaxy when seen from Earth. This region, where the Milky Way's disk blocks our view, is called the Zone of Avoidance. Bright stars, thick dust lanes, and gas clouds in our own galaxy overwhelm the faint light from distant sources, while interstellar material absorbs and scatters much of what tries to get through. To peer into such areas, astronomers rely on wavelengths like infrared and radio, which can slip more easily through the obscuring veils. Even with those tools, our view remains partial. Still, infrared surveys have revealed some of the outline of the Taurus Void. Its diameter appears to be around 200 million light-years, with its center about 150 million light-years away. When we look in that direction, one of the striking features is the contrast, a region with relatively few galaxies adjacent to a rich concentration of them. On the far side of the void, the Perseus-Pisces supercluster stands out as one of the largest and brightest galaxy chains in that part of the sky. The transition from the emptier region to the crowded Perseus-Pisces complex is unexpectedly sharp. It almost looks like a wall, a boundary where a dark, underpopulated volume ends and a bright, structured mass of galaxies begins. In other contexts, such sharp edges can hint at dust, clouds, or other obscuring material, but infrared studies do not support the idea that this sharpness is due simply to foreground dust. It seems more likely that gravity itself has sculpted this dividing line over time, pulling matter strongly toward the supercluster and leaving the adjacent region more depleted. Even so, the Taurus Void is not perfectly empty. Subtle distortions in the light from background galaxies, as well as other gravitational signatures, suggest that there is unseen mass within it. This may take the form of diffuse gas and dust, extremely thin clouds that have not yet collapsed into stars or galaxies. Some astronomers speculate that such clouds could be the raw material for future galaxies, slowly cooling and evolving in the deep quiet. Others point out that dark matter, the mysterious component that makes up most of the universe's mass, must be present to some degree as well, shaping the paths of any light that passes through. More adventurous ideas go further, proposing that void centers might host clumps of exotic forms of matter, antimatter clouds, or even matter with effectively negative mass, which would repel instead of attract. These concepts, while intriguing, remain outside the mainstream of accepted physics. They are difficult to test and do not yet fit comfortably into the well-checked framework of current theories. For now, such suggestions serve more as reminders of how much we still do not know than as solid descriptions of what is actually there. At present, only 2 galaxies have been clearly identified as residing deep within this enormous void. One, UGC 2627, is a spiral galaxy that in some ways resembles a smaller version of our own thin disk, gentle arms, a sprinkling of star-forming regions. The other, UGC 2629, is a faint elliptical dwarf, more like a smooth ball of stars with little visible structure. These 2 neighbors are separated by only a few 100,000 light-years, a small distance compared to their nearly 185 million light-year distance from us. They share a loneliness that is hard to picture, drifting together in a region where nearby galaxies are rare. It is entirely possible that more such galaxies exist in the Taurus Void but remain hidden from our current surveys, concealed behind the Milky Way's bright disk, or simply too faint and diffuse to pick out easily. As instruments improve and deeper, wider surveys are carried out in infrared and radio. Some of those missing neighbors may slowly reveal themselves, adding detail to the map of this vast emptiness. Zooming back out, the Virgo supercluster is not an isolated island. Together with several other nearby superclusters, it belongs to an even larger structure, a gigantic galactic filament known as Laniakea. The name means immense heaven, and it feels fitting. Laniakea contains on the order of 100,000 galaxies and stretches over more than 500 million light-years of space. It is not a rigid object, but rather a region where the motions of galaxies are influenced by a common gravitational landscape, streaming slowly towards certain dense centers. At the heart of this pattern lies something astronomers call the Great Attractor, a region of unusually strong gravity located about 250 million light-years from Earth. It is not a single galaxy, but an extended, massive concentration of clusters and dark matter. The Great Attractor tugs on galaxies across Laniakea, including our own. The Milky Way, Andromeda, and countless others are all drifting, almost imperceptibly, in its direction, carried along by the subtle pull of mass on larger and larger scales. From our quiet vantage point, orbiting a yellow star in one arm of a spiral galaxy, all of this is happening at once. NGC 6503 brightens slowly as it falls toward richer gas. Voids expand, clusters loosen, superclusters stretch, and filaments like Laniakea whisper their shapes into the motions of galaxies. We sit in the middle of these flows without feeling them in our bones. Yet when we look up at the night sky, in the dim glow between the stars, we are seeing just enough to sense the immense pattern. We are part of a universe stitched together not only by matter and light, but by vast, patient, empty spaces in between. When astronomers map out the motions of galaxies across Laniakea, something subtle but striking appears. All these immense rivers of stars, including our own Milky Way and the Virgo supercluster, seem to be flowing together through a much larger landscape, one that is not uniformly filled with galaxies, but carved with enormous hollows. Beyond the familiar clusters and filaments, the pattern thins out into an almost featureless dark, a blackness so wide that the light of distant galaxies is swallowed by sheer distance and emptiness. Even neutrinos, those almost weightless, elusive particles that pass through whole planets as if they were mist, would need billions of years to traverse such a span. It feels almost unbelievable that a structure on this scale went unnoticed until quite recently. Only about a decade ago, in 2013, a team of astronomers at the University of Wisconsin-Madison, led by Amy Barger, was carefully measuring distances to galaxies in our region of the universe. Their goal was straightforward: to refine our map of where galaxies are and how fast they are moving. But as they compared positions and motions, a surprising pattern emerged. Laniakea and many of the surrounding superclusters seemed to sit inside a region less crowded with galaxies than expected, a huge, gently underdense bubble in the cosmic web. When they ran the numbers, the scale of this bubble turned out to be astonishing. Its diameter appeared to exceed that of any previously known void. The implications were unsettling enough that they nudged at some basic assumptions about how evenly matter should be spread on the largest scales. The universe, it seemed, might be more intricate and clumpy than many models had assumed. The work by Amy Barger, Ryan Keenan, and Lennox Cowie pointed to the existence of what is now called the KBC supervoid, named from the initials of its discoverers. According to their analysis, this giant region is roughly spherical in overall shape, though not perfectly so, and its diameter may reach or even exceed 2 billion light-years. The Milky Way appears to sit not at the exact center, but somewhat offset, perhaps a few 100 million light-years from the void's notional middle, and a similar distance from its outer edge. We live, in other words, not only in a galaxy, not only in a supercluster and a vast filament, but also inside a faintly underfilled bubble in the universe's matter distribution. This discovery did more than add a new name to the cosmic map. It helped shed light on a long-standing tension in cosmology. For many years, astronomers had noticed that measurements of the universe's expansion rate in the Hubble constant gave slightly different answers depending on how they were made. When they used relatively nearby galaxies and supernovae as yardsticks, the calculated expansion seemed faster than when they used the cosmic microwave background and very distant galaxies as reference points. The discrepancy was small but persistent, and it refused to go away as instruments improved. If our region of space is part of a large, gently underdense supervoid, that difference begins to make more sense. Galaxies inside such a void, including our own, feel a net gravitational pull from the matter concentrated beyond its edges. That extra tug subtly stretches the local distribution of galaxies, adding to their apparent motion away from one another. When we measure expansion using nearby galaxies, we are inadvertently sampling a region where motions are influenced by this imbalance. From farther away, where the influence of the void is averaged, together with many other structures, the expansion rate appears slightly different. The KBC supervoid may not solve the entire Hubble tension on its own, but it provides an important piece of the puzzle. One of the intriguing aspects of this supervoid is that it is not empty in the way smaller voids are often imagined. Within its volume lie not only galaxy filaments and clusters, but also smaller voids, such as the local void in the Taurus void we wandered through earlier. Compared to the densest parts of the cosmic web, the KBC region has fewer galaxies and less matter overall, but compared to truly deep voids, it is relatively rich. It is, in a sense, a hollow that contains its own internal structure, thin threads of galaxies, tiny island groups, and their own pockets of emptiness nested within. Even so, when we set the KBC supervoid against the backdrop of the entire observable universe, it shrinks somewhat in our imagination. The observable universe spans roughly 92 billion light-years across. Against that expanse, a 2 billion light-year void is large, but not dominant. On maps that show structure at the grandest scales, the KBC region appears as one dark blot among many, a slightly dim patch on a sky full of faint modeling. Most voids are comfortably explained by our current theories of cosmic evolution, but some stand out with properties that still puzzle us. One of the most intriguing of these outliers is known as the Eridanus supervoid, more commonly called the CMB cold spot. This region appears to span anywhere from 500 million to a billion light-years and lies billions of light-years from the Milky Way at a distance somewhere between 6 and 10 billion light-years. That makes it not only far away in space, but also far back in time. When we look toward it, we are seeing light that began its journey when the universe was much younger than it is now. The cold spot sits in the southern half of Earth's sky and covers an area several times larger than the full moon. Yet, you cannot see it by eye, even on the clearest, darkest night. It does not reveal itself as a gap in the stars or a patch of missing galaxies. Instead, it shows up only when we look at the universe in microwaves, at the faint afterglow of the Big Bang, the cosmic microwave background. In maps of that relic radiation, the cold spot appears as an area where the temperature is slightly lower than average by about 70 microkelvin. That difference is minute, just 70 millionths of a degree, but it is meaningful. It is roughly 4 times stronger than the next largest temperature anomaly in the cosmic microwave background, and its sheer size makes it difficult to ignore. Many smaller fluctuations in the CMB are naturally explained as ripples left behind by quantum fluctuations in the early universe, stretched to cosmic scales by inflation. But the cold spot, with its depth and extent, has proven a more stubborn riddle. One explanation suggests that as CMB photons travel through space, they are influenced by the gravitational fields of large-scale structures. They pass clusters, filaments, and voids. Passing through dense regions can slightly change their energy, and traveling through large, underdense regions can do the same in the opposite direction. This integrated gravitational effect can cause some areas of the CMB sky to appear a bit cooler or warmer than others. If the cold spot sits along a line of sight that includes a particularly large and deep void, that might help account for its unusual temperature. However, detailed calculations indicate that the known structures along that path can only explain a portion of the observed cooling, perhaps around a quarter of the total effect. The remaining difference seems too large to be easily accounted for by ordinary matter and gravity alone. That has led some scientists to speculate that dark matter distributions or even dark energy fluctuations in that region might play a role. Others have proposed more exotic ideas, from unusual early universe physics to statistical flukes. For now, the cold spot stands as an open question, a small, quiet reminder on the cosmic microwave map that there are still corners of the sky we do not fully understand. As we follow these threads from harsh exoplanets to dying stars, from blazing Wolf-Rayet suns to black holes and vast voids, a certain pattern emerges. Space, for all its beauty, is not a gentle place. Even in our own world, teeming with life, there are regions that are hostile to most creatures. Deep ocean trenches, polar deserts, volcanic slopes. On other worlds, the dangers are greater and more varied. Diamond-hard gravity, glass storms, lava seas, lethal radiation, and darkness so complete that even light cannot escape. Further out, the threats become more abstract. Places where matter is crushed beyond familiar states or swept aside entirely, leaving only emptiness on scales that are hard to feel. There may be objects in regions more dangerous, more extreme, and more mysterious than any we have yet detected, still hiding beyond the reach of our telescopes. The universe is wide enough and old enough to hold surprises we have not even thought to name. Yet, woven through all of this is a different kind of comfort. The more we learn about these distant, inhospitable places, the more sharply our own circumstances come into focus. We see how delicate it is to have liquid water, a stable atmosphere, and a star that neither strips our planet nor shatters it. We notice how rare it is, in a universe of extremes, to find a narrow band where life can persist long enough to ask questions about the stars. Lying beneath our own sky, we are far from lava oceans, pulsar winds, and supermassive black holes. The nearest voids and supervoids are not empty holes waiting to swallow us, but vast, silent rooms in a house we are only beginning to map. From here, their dangers arrive only as faint signals, a cold patch in the microwave background, a small discrepancy in how fast galaxies drift apart, a tiny wiggle in starlight or in space-time itself. In that sense, learning about the most dangerous objects and deepest abysses in the cosmos is less about seeking fear and more about tracing the edges of possibility. Each hostile world, each collapsing star, each dark hollow in the cosmic web shows us another way matter and energy can arrange themselves, another possibility that did not happen here on this small, temperate planet. And as we listen to these stories in the quiet of the night, our place in that immense arrangement feels, if anything, a little more precious, and the distant darkness a little less unknowable.